Ladies and gentlemen, welcome back to our second session of the day. We will proceed to the presentation by Mr. Franklin To, entitled A Comparison of Empirical and Numerical Approaches for Estimating Rock Support Pressure on Tunnel Lining. Mr. Franklin To is a chartered engineer with 6 years of working experience in civil and geotechnical engineering. Franklin is now a project engineer with the tunnel and cavern team at AECOM in Hong Kong. Please welcome Mr. Franklin To.
Hi everyone, my name is Franklin. I'm from Hong Kong. I'm now working as a project engineer of the tunnel team in AECOM. Today, it is my pleasure to present you my topic, which is a comparison of empirical and numerical approaches for estimating the rock support pressure on tunnel lining. Today's presentation is divided into 4 parts. First of all, I'll introduce you guys the background of this study. Then I will quickly go through some previous lectures. After that, I will talk about the methodology for this study. And finally comes to the results and discussions. So first of all, the introduction. Hong Kong is a densely populated city with 7.5 million of population. However, there is only less than 25% of the total land area is developed. This is because the remaining areas and highlighted in these red boundaries are surrounded by hilly terrains, rural areas, and statutory protected areas. 85% of these hilly terrains are underlain by hard and massive igneous rock, such as the granite and volcanic tuff. They are favorable for underground space development, such as the rock tunnels and rock caverns. Indeed, many railways and highways in Hong Kong were constructed in form of tunnels, such as the Lion Rock Tunnel on the left, the Taikus MTR station on the middle. Most of them are supported by the permanent cast-in-situ concrete lining on the right. Design loadings include the self-weight, rock support pressure, rock wedge, groundwater, internal facilities, and etc. Among these loadings, the estimation of rock support pressure is the most uncertain factor because it cannot be simply measured and well proved. If the design thickness of the concrete lining can be optimized, the overall construction cost and time can be significantly reduced. So what is the rock support pressure? Let's excavate a new rock tunnel in Hong Kong. Before excavation, the stresses are downward due to gravity by the overburden pressure. However, after excavation, the stresses are redistributed. These loosened rock art will exert a rock support pressure, and as engineers, we need to design this support. According to GeoGuide 4, which is a guide to cavern engineering published by the Hong Kong government, the source of loadings should be either accounted for by an empirical method or an analytical or numerical assessment. So what are they? Empirical approaches correlates the relationship by observation or experiment. For example, if you get a group of data, you can get an equation with the best fit line of y equal to mx plus c. On the other hand, for numerical modeling, you solve problems by numerical approximation, such as computer modeling with the finite element method or the discrete element method. So for rock tunnel design, there are 2 major types of parameters. The first one is the geotechnical conditions, such as how strong or weak the rock is. The second one is the tunnel arrangement, such as how deep and wide we need. So the question to ask today is, are geotechnical engineers estimating the rock support pressure with full considerations of these parameters? By establishing a series of comparison models, this study aims to study the rock mass behavior around the excavation profile, investigate the difference in the estimated rock support pressure using empirical approaches and finite element model, Due to the time limitation, I'll only talk about the study on the Tasaki's and Barton's one for the empirical approaches, and only on the ground pressure from the finite element modeling. And finally, study the influence of missing parameters in empirical equations. So, literature review. Before going into details, I would like to first quickly introduce some basic terminology of rock tunneling to you. First of all, the tunnel width, which is the maximum width of excavated profile, including the tunnel lining. Uniaxial compressive strength for the UCS, which is a mechanical strength of intact rock under compression. Young modulus, which is the elastic deformation resistance of intact rock under stress changes. Poisson ratio, which is the ratio of lateral strength divided by actual strength. In situ stress ratio, the K value, which is the ratio of horizontal stress divided by the vertical stress. And the higher K value means the higher horizontal stresses. The elastic and plastic zone. So after excavation, the rock far away remains elastic, while the rock near the excavation are free to deform and use. The NGIQ system by Barton. So this number quantify how good or bad the rock is by multiplying these 6 rock parameters. These are 2 examples showing the Q value of 25 for good rock and Q equal to 1.59, which is a poor rock. Finally, the rock arching theory. The rock arch can actually self-stand by utilizing this hoop, or we say the compressive stresses. I have extracted some important highlights of previous empirical study. The most commonly adopted one in Hong Kong is the Tasaki's rock arching theory in 1946 and Barton's Q system in 1974. These studies were carried out by collecting the field data of relatively small tunnel, and the design loadings are actually from the back analysis of installed tunnel supports. And the concept of rock arching theory was proposed. So instead of taking all these ground loadings, the full overburden pressure up to the ground surface, tunnel is only taking the loading from this loosened rock arch zone by considering the arching effect. They are very fast and easy to use, and therefore they are still widely used in the world nowadays. This shows the input parameters into the empirical equations by Tasaki and Barton. As you can see, the UCS have been considered somehow in the SRF by Barton. The tunnel width have been considered by Tasaki, and both these approaches have considered the rock mass quality. However, none of them have considered Young modulus, Poisson ratio, in situ stress ratio, and also the tunnel depth. On the other hand, numerical modeling can be used to handle engineering problems with great complexity, such as the surcharge, complex geology, inference to existing tunnel, excavation sequence, composite structures, and the 3D problems. So, methodology. The first thing is model setup. Comparison models were established using the software by Rock Science, which is the phase 2. So something to mention is that all geotechnical software in Hong Kong to be used for the design works has to be pre-approved by the Hong Kong engineering government authorities. The geotechnical and geological parameters and also the tunnel profile are based on the Hong Kong Highway project. So there are 4 stages of modeling. Stage 1 is the initial stage. Stage 2 is the excavation stage. Stage 3 is the support installation. And stage 4 is the full excavation. The tunnel span is approximately 13.5 meters. And the tunnel depth is 8 times the excavation span, which is approximately 110 meters. These are the baseline parameters. The UCS is 75 MPa, Young modulus is 30,000 MPa. The Poisson ratio is 0.3. And the Q value is 10, which is fair to good rock. This study is divided into two parts. The first one is the rock properties which we cannot control, including the UCS, Young modulus, Poisson ratio, in-situ stress ratio, and the rock mass quality. The second part is the tunnel arrangement which engineers can actually control, which is the tunnel depth and the tunnel width. This is a summary table summarizing the baseline and varying parameters. These are some assumptions and limitations. The first one is that the rock mass is modeled as a continuum instead of discontinuum. The second one is that the rock wedges are considered separately. The common practice in Hong Kong is to estimate the rock wedge pressure by separately using a kinematic software such as the unwedge, by assigning the major joint sets information, the deep angle and deep directions, and also the rock joint shear strength such as the C phi. The stress field is only by the rock overburden loading, so there are no tectonic stress or other loading considered. Also, the permanent support are installed right after the tunnel excavation. There are no structural contribution by the temporary support, which is also one of the major design guidelines or requirements in Hong Kong. Also, the groundwater is considered separately because another approach commonly adopted in Hong Kong is to apply the groundwater pressure separately into the structural model. And finally, with the advanced technology, we assume excellent and controlled blasting, and therefore there is no stress disturbance to the rock mass. Finally, the results and discussions. First of all, the rock arching after the tunnel excavation. So before excavation, the principal stress orientation are vertical and horizontal, governed by the gravity. After excavation, the major principal stresses orientation now changes to be surrounding the opening. And by observing the change in color from blue to green, we can observe the rock arching zone. Also, when we look at the strength factor, so near the excavated profile, the strength factor is around 1. And when the rock mass is away from the opening, it increased radially from the orange color to yellow and finally to the green color. So we also observe the rock arching zone here. So what we see here is different rock arching zones were identified by looking at the principal stress orientation and strength factor. And therefore, the numerical modeling actually verified the rock arching theory proposed in 1946. These shows the stress contour at different tunnel depth by the multipliers of excavation span D from 1D to 15D. Similarly, the rock arching zones were observed in these compression models. This implies that the permanent lining of a rock tunnel at the moderate depth is only supporting the loosened rock mass after excavation instead of the full overburden pressure to the ground surface. However, by carefully looking at the color of stress contours, we can see at the 15D, they are more green and yellow color. We can observe a slow increasing trend of the support pressure with the increasing tunnel depth. This shows the plastic zone development around the excavation profile at different tunnel depth from 1D, 5D, 7D, 9D, 12D, and 15D from the upper left to the bottom right. So we can see that the extent of plastic zone increased with the depth. The plastic zone first developed at the two sharp corners near the invert level, and then the crown, and finally the wall and the invert, and eventually the entire excavation profile. This shows the plastic zone development for different rock mass quality, from Q equal to 0.1, which is very poor rock, increasing until the Q equal to 40, which is very good rock. Obviously, the excavation in poor rock gets more plastic zone. When the rock mass quality increases, the plastic zone disappears first at the wall and invert, and then the crown. But even for very good rock conditions, the plastic zone still exist at the sharp corners near the two invert, where we get the stress concentration due to the horseshoe profile. So these graphs show the relationship of rock support pressure at crown with different UCS, yard modulus, Poisson ratio, in-situ stress ratio, rock mass quality, tunnel depth, and tunnel width. The red color is the results from the final element model. The orange one is from Tazaki, and the green one is from Barton. As you can see, final elements estimation in red color are smaller than all from empirical approaches, except the middle one with poor rock quality. Barton's estimation in green color is the closest one to the final element modeling. And Tasaki's estimation in the orange seems to be too conservative because it is much larger than the results from the final element model. So in general, we observe that the UCS, yard modulus, Poisson ratio, and the tunnel width are not significantly affecting the rock support pressure at crown. And on the other hand, the in-situ stress ratio, rock mass quality, and the tunnel width are quite sensitive to the rock support pressure at crown. For UCS, there is no change because the rock strength is much larger than the in-situ stress at a moderated depth of 200 meters. For yard modulus and Poisson ratio, there are also no change because they are purely deformation parameters. For the in-situ stress ratio, actually no clear trend was interpreted. According to the Geoguide 4, the common range of K value in Hong Kong is between 1 to 2.5. Within this range, the numerical modeling shows an increasing trend, actually. For rock mass quality, it indicates an exponential decay function, and at very poor to poor rock conditions, the estimated pressure by numerical modeling was larger than that by empirical approaches. However, this may be due to the wrong application of the same ground relaxation and the same lining stiffness for different ground conditions, which lead to an excessive ground deformation and eventually the failure. A detailed study could be carried out for further investigation. For tunnel depth, we observe a slow increasing trend. However, the estimated pressure at tunnel depth of about 200 meters was still smaller than all empirical approaches. And the estimation by the Barton is still therefore conservative to be adopted for a tunnel length and a moderated depth. For tunnel width, some previous studies confirmed that it affects the pressure only when a flat tunnel roof was used or at a very poor rock conditions. This result shows that the influence of tunnel width for horseshoe profile to the pressure is actually not significant. Finally, the conclusions and recommendation. First of all, empirical approaches are conservative to estimate the rock support pressure at crown, but they could be too conservative, which means not cost-effective in some cases, such as the adoption of Tasaki's rock arching theory. Therefore, they are suitable for preliminary design. Numerical modeling should be used for design optimization during the detailed design stage to save the construction cost and time when more GI data is available. This shows the summary table of influence of different rock parameters to the rock support pressure at crown. So as we can see, UCS, yard modulus, Poisson ratio, and tunnel width, they are not significant. But for the in-situ stress ratio, rock mass quality, and tunnel depth, they are quite sensitive. Therefore, considerations should be given when we plan the GI. And some interesting fact is that we usually order a lot of lab tests for the UCS, yard modulus, and Poisson ratio. However, they are not very useful to estimate the rock support pressure, so therefore it is a good chance for us to revisit which kind of GI we really need. For the initial stress ratio, it involves very expensive field tests, but I do suggest to carry out a field if we are doing a large-scale tunnel project. For rock mass quality, we could carry out the HDC, which is the horizontal directional coring along the tunnel alignment, so that we can have a better understanding on the overall rock mass quality, especially the location for different fault zones. Tunnel depth, as a geotechnical engineer, to be honest, nothing we can really do because it is somehow governed by the transportation arrangement, such as the tunnel portals have to connect different roads and different traffic sightline requirements. Finally, for the tunnel depth, although it gives the same rock support pressure, during the structural analysis, we will eventually get a higher bending moment. So therefore, we still have to carefully look at what tunnel width we actually need. So that's the end of my presentation. Feel free to ask if you have any questions.
Thank you, Mr. Franklin To, for your presentation. Ladies and gentlemen, please be informed that you may pose your questions to the speaker via the Q&A function at the bottom of your Zoom interface. Our next presentation, entitled On How Blowout in Tunneling and a Case Study in Ho Chi Minh Metro Line 1, will be presented by Dr. Min Yan Wu, who is a lecturer in Department of Infrastructure Engineering, Hanoi University of Mining and Geology, Vietnam. He also worked as a consultant for some projects in Vietnam in underground construction such as tunneling and pipe jacking. Please welcome Dr. Min Yan Wu.